Hello again, and here with me I have Julien Jakubowski, who's going to talk to us about Apache Pulsar. Finally, an alternative to Kafka? Question mark. Let's see how the question is going to unravel in the next 40 minutes. And over to you, Julien.
Thank you. So, hello everyone. Thank you for attending my talk. So today, when you need a data streaming platform, what probably comes to mind is Apache Kafka. And if you've been using Kafka for a while, you might be facing some limitations or pain points in your daily operations, such as a lack of flexibility when you need elasticity, when you need to scale. And additionally, maintaining a Kafka cluster can be very expensive in terms of network and storage costs. And also, if you're using traditional message bus solutions like RabbitMQ, for example, you might also be facing certain limits. But I have good news for you. There is an alternative that is gaining popularity, Apache Pulsar. By the end of this talk, you will have discovered how Pulsar differs from Kafka and traditional MQ solutions, and hopefully you will want to try it out for yourself to make your own opinion. So a few words about me. I'm a developer advocate in Europe. I work at String Native, a managed Apache Pulsar provider. I've been a software engineer for more than 20 years now, mostly using Java and Spring. I've built distributed, scalable, and event-driven systems for several industries, including retail and financial services. I live in Lille, in north of France, and I'm one of the leaders and founders of several developers communities, such as the Java user group of Lille, for example. So feel free to use the QR code to join me on LinkedIn, and you can also follow me on Twitter. So what is Apache Pulsar? Apache Pulsar is a cloud-native messaging and data streaming platform. So, well, I'm throwing out some jargon here, but don't worry, I'll explain it right away. So cloud-native means that Pulsar is designed for running in containerized environments. It's designed to run on Docker and Kubernetes and all that stuff. But cloud-native also means elasticity. On an elastic system, you can add resources quickly to adapt to a growing workload, and you can also remove resources when the workload decreases to save on cost. You will see in this talk that elasticity is one of the main things that make Pulsar stand out. And Pulsar is both a messaging and a data streaming platform, as we will see in this presentation. So I'm going to explain those words as well, what is messaging and what is data streaming. So Pulsar is a messaging and streaming platform, but what is data streaming? Data streaming is the process of transmitting data continuously and in real time from a source to a destination. So the data is sent in small pieces and is processed or analyzed as received. These small records, these small pieces, are often called events. Events because they typically represent something that happened in the past. For example, my stock level at 10 a.m. was 42, and at 11 a.m. it was 41. So these are two events. And in the context of data streaming, the events must be processed in the correct order. They are interlinked. If they are not processed in the correct order, something will be broken and bugs will be created. These data, these events, they may be transformed, aggregated, or replayed. And this is why you may need to persist the data for a long time. You may also need to read millions of records very quickly and perform big catch-up reads, right? So you need throughput. These platforms can handle a large amount of data and can process thousands of messages per second. So they can scale horizontally, which means they can manage workloads that are too large for a single node to process. And they do that by spreading the workload across multiple nodes. So the goal is to process these data streams. And typical stream processing use cases include data ingestion. That's the process of collecting and importing data from various sources for storage or processing and analysis. And other use cases can be about real-time analytics. Real-time analytics is about making the right decisions based on fresh data. So that's when you don't want to wait for a batch process to be run tomorrow. You need to make the decision right now on fresh data. For example, if you need to implement a dashboard that is updated in real time, or when you need to implement fraud detection, right? So the most common streaming platforms is Kafka, but I can also mention Amazon Kinesis in the managed world, and of course, Pulsar is a great streaming platform. Now, let's talk about messaging, and message queuing is quite different. There are some similarities. There are producers and consumers, and a first-in, first-out structure that we can call queue or topic, but the goals are completely different. Let's say that sometimes a service needs a task or several tasks to be done, but it can't run then this task itself for various reasons. Maybe the task takes too long, or it can be implemented within the service for many reasons. For example, this could be, an e-commerce website, an online selling website that sometimes need to perform a long-running payment task, or let's say call an AI, right? Some long-running task. So the service can delegate the task execution to another service by sending to this service a command. So the service sending the command is the producer, and the one executing the command is the consumer. And the producer can't wait for the task to be completed, because this task might take a while and could also fail. That's why we need to decouple the producer and the consumer. And we also need to ensure reliable execution, making sure that the task eventually gets done, even if it initially fails. To do that, you can set up a work queue. So this queue contains messages from the producers, and each of these messages is a task to be performed by consumer instances. So message broker manages this message queue, accepts the producer messages, and delivers them to the consumer instances so they can perform the task. The broker distributes the messages among the instances to balance the load across them. So task 1 will be consumed by instance 1, task 2 is consumed by instance 2, and so on. And you don't need to perform this task in a strict order. For example, let's say the task involves payment validation for an online store, for example. And let's say that you have two customers, Alice and Bob, and Alice placed an order 2 seconds before Bob. Then it's not a big deal if I validate Bob's payment first. It's not a big deal, right? Unlike when you stream data, because when streaming data, breaking the order causes problems. But in message queuing, it's not such a big deal. So it means that the expectations for message queuing are different from those for data streaming. So queues can grow faster than consumers can handle. So one expected feature is the ability to add new consumers to consume the queue faster, and also remove those consumers when the workload decreases to save on cost. Another expectation is when a consumer is busy processing a message, you don't want to wait for the processing to be completed. The broker will deliver the next task to another consumer instance without waiting for the current task to be complete. When the consumer fails to handle a message, because there is an error or timeout, you may need the message broker to redeliver the message later to retry the task, right? And you also need to remove some messages that can be, undeliverable. These undeliverable messages, you need to remove them from the queue and move them to a dead letter queue. So because of that, messages may then be consumed in a slightly different order than produced. But as we said, the order is not a strong requirement here. So RabbitMQ and Amazon SQS match these requirements, these semantics, because they implement the message queue semantic. And we cannot expect the requirements from a streaming platform. These platforms are not designed for that. However, Pulsar implements both the streaming requirements and the message queuing requirements, as we will see. So data streaming and messaging require a different set of features. So for the data streaming requirements, you need the data to be processed in order. That's not a big deal in the messaging world. For the data streaming requirements, you need to ingest large amount of data. You need data retention, but RabbitMQ and other traditional message brokers are not designed to retain large amount of data. Kafka is designed to retain large amount of data, but not quite, as we will see later. Kafka is designed to handle catch-up reads. That's not the case for RabbitMQ because they are not designed to retain a large amount of data. And on the right side, you need to add or remove consumer dynamically. Kafka is not very good at that, for doing that. On the right side, for the messaging queuing, you don't want to block the queue when the consumer is busy or fails. So it means that RabbitMQ is quite good at managing that. That's not quite the case for Kafka. And you also need to redeliver failed messages later. So on the left, that's where Kafka is good at, while on the right, that's for RabbitMQ, ActiveMQ, and all those traditional message queue broker. So many companies end up with these two different technologies for these two use cases, meaning two different broker technologies to operate in production and two different SDK to learn for developers. So now you could say, well, why not use Kafka to implement a message queue? Because, Kafka is also about producing and consuming messages, right? So you may think using a streaming platform to implement a work queue is a good idea. I used to think that, but when I try to do that, well, that looks a bit like this, right? So I've done my best, but I realized that Kafka is not designed for that. So let's try to do that together right now. But first, let's explain how it works with an MQ broker like RabbitMQ or ActiveMQ. So here we have a producer and a consumer. We are in a simple scenario with a single consumer instance consuming messages from the queue. Now, what if I need to consume my messages faster? I will then add a new consumer instance. The message broker will then distribute the delivery of messages among the instances. It's automatic. I don't need to do anything on the broker side. I just need to scale up my consumer system or to scale out my consumer system. Now the messages are consumed twice as fast because I have doubled the processing power on the consumer side. So that's pretty straightforward. What if there is an incident now? For example, a message causes a consumer instance to crash, or the task corresponding to the message takes too long. Then I'll be able to retry delivering the messages easily. The messages that comes after the problematic one will still be processed, so the queue won't get blocked. The broker will just try to deliver the faulty messages again a bit later. So this might cause the messages to be processed out of order, but as we mentioned earlier, that's not a big deal for messaging, unlike data streaming. Okay, and what if a message is completely invalid? It's a message that I will never be able to consume, for example, because it has, I don't know, an invalid format, or because I've retried consuming too many times. In that case, the broker will remove the message from the queue and move it to a dead letter queue. So the queue is unblocked, the main queue is unblocked, and we can review the faulty message later to investigate and to figure out why it wasn't consumed. Now, let's try that with Kafka. So we start simple with one topic composed of one single partition and one single consumer instance. I'm not including the replicas in my diagram to keep my explanations as clear as possible. So now let's say that I need to consume the queue faster because the queue is growing too quickly. Then I need to add a new worker, a new instance, a new consumer to the Kafka consumer group. However, when you need to add a new active consumer to the same consumer group in Kafka, then you need to add a new partition to the topic, because you can't have more active consumer instances than partitions. However, adding a new partition to a topic is far from being trivial. It involves reorganizing the data in the topic, and if there is a lot of it, this can be a long, tedious, and costly operation. It also requires an operation on the broker side, which is often managed by another team, meaning that we need to coordinate with that team, and that's not always very quick. On the other hand, with an MQ broker, I just need to add a new consumer, and that's it. Now, what if a message can't be consumed because it's invalid, meaning I'll never be able to process it? This situation is called a poison pill. It blocks the queue, and there aren't many options in Kafka. One approach is to manually adjust the consumer group offset to try to skip the invalid message, but that's a bit tricky, and that's often manual operation, a manual process. So the other option is to add a new consumer. However, to scale up consumers, I need to add a new partition on the broker side, which brings us back to the same problem as before. Okay, so what if I plan two partitions? That should prevent these issues, right? Or maybe not. So now I have my two partitions and my two active consumers. We are about to find out if the problem is solved or not. Let's say that one message blocks the queue again. Then task from partition 1 will be processed, which is better, but partition 0 is still blocked. So you have to wait for consumer 0 to finish before processing the remaining task in partition 0. So the problem is not really solved here. All right, so I intended to illustrate that using a data streaming platform for message queuing is not ideal. These platforms are not designed for that. This is not the same use case, not the same semantics. Messaging is what message brokers, such as RabbitMQ, are designed for. Does it mean that you have to choose between messaging and streaming? Or do you have to manage two different platforms, one for messaging and another for data streaming? Well, with Pulsar, this is not a dilemma. You can do both using the same platform, the same technologies. So you have only one SDK to learn, and you have only one broker to manage in production. Pulsar is indeed a unified messaging and streaming platform. This is one of the key features of Pulsar. Now I want to talk about Pulsar scalability and elasticity. Scalability and elasticity is different. Elasticity means you can grow or shrink resources quickly to adapt to workload changes. So you can save infrastructure costs by avoiding over-provisioning. So some data streaming platforms like Kafka and Pulsar can scale very well, but Pulsar is both scalable and elastic. The scalability requirements are determined by the bottleneck you have to address at a given time. So if a bottleneck is the number of messages remaining to be consumed in a topic, then you need to scale on the consumer side. When the bottleneck is the number of topics or the number of connections with clients, then you need to add more processing power to the Pulsar cluster. And when the bottleneck is the storage capacity, well, then you just need to add more storage capacity to your cluster, right? So let's dive into the first bottleneck, which is likely to be the most common one you will encounter. Suppose you have multiple consumers consuming a topic. What happens if the number of messages to be consumed grows faster than the consumers can process them? Then with Pulsar, you just have to add new consumers to what we call a shared or key shared subscription. So you can increase the throughput by adding new consumers. With Kafka, when you need to add a new active consumer to the same consumer group, you need to add a new partition to the topic. That can be painful, as I said, so you have to anticipate and plan carefully. But Pulsar doesn't have this issue. And of course, when you have fewer messages, you may end up with underutilized consumers, so you can also remove them to save infrastructure costs. Moreover, and that's super cool, if you use the Pulsar key shared subscription feature, you can benefit from this consumer elasticity while preserving the ordering guarantee. So you've got the best of both worlds, right? Unlike traditional messaging brokers. That is super cool. Now that we explored the most common bottleneck, let's explore how Pulsar can handle a rapidly increasing number of consumers and producers. But first, I need to explain the unique architecture of Pulsar. This architecture is more sophisticated than other platforms, so it brings many benefits. In Pulsar, there are two types of nodes, the broker nodes and the bookie nodes. The broker nodes are responsible for managing all the communication and the processing of the topics, so they are stateless. They don't store data. So broker node deletion won't impact the data. In contrast, the bookies nodes are responsible for storage. They have state, they store the messages. The bookies are Apache Bookkeepers nodes. So let's say that I need more processing power on my cluster. I'll add more broker nodes. And that's it. Because their state is stored in the bookkeeper tier, I can add a new broker node, and that load is migrated to another broker node. So basically, you just add new broker nodes, and boom, you're done. So some of the magic of Pulsar is that it will take care of all the moving of connections, and the moving is transparent to your application. If you compare this to Kafka, with Kafka, you will have to add a new broker, you will have to manage the movement of all the data to another broker for it to rebalance it, because in Kafka, storage and processing are coupled. In contrast with Pulsar, that's decoupled, and you just have to add a new broker node, and voila, it's done. Much easier. And when we need to store more data, then we'll just add more bookies. As soon as you add a new bookie node, it's going to be eligible for getting new messages right away. It immediately becomes functional. There is no data movement. Pulsar does not have this issue when you need scalability on your data. So how is all this possible? Is it magic? Nope. It's thanks to the partition-free storage model of Pulsar. So let me explain it right now. As a reminder, here is the Kafka storage model. So messages are sent to a topic, which is a first in, first out structure that holds these messages. The messages are distributed across multiple partitions. Each partition is stored and managed on a separate node to enable scalability. Kafka guarantees that messages are consumed in the same order in which they were written to the partition. New messages are distributed across partitions, either in a round-robin manner or using a key. In the latter case, all messages with the same key will end up on the same partition, allowing messages with the same key to be consumed in the correct order. So what does this design imply? Well, imagine you have a broker in this situation, a cluster in this situation, a Kafka cluster. Let's say that you have three topics. One is divided into three partitions. The second is also divided into three partitions, and the third has only one partition. I'll disregard, replicas for the sake of simplicity. Now, let's say that you need to add a fourth topic that will consume quite a bit of data. A topic D here in red. The topic is growing. It keeps growing, and then what happens? The left node crashes because its disk is full. But it's a shame because the total available storage capacity on the cluster is actually enough to store the data. But this issue happened just because of how the partitions are spread across the nodes. With Kafka, I often have to worry about how partitions are distributed across different disks and nodes. I need to worry about these details. I need to manage and anticipate this problem. There is a lot more planning indeed. There is a lot more planning needed with Kafka compared to Pulsar. So life of a Kafka administrator can be a bit complicated. What if I could have done this? What I could have done to avoid this problem? And that would have been to move topic C to another node before adding topic D. Depending on the amount of data involved, this can consume a lot of network and IO resources and take a lot of time. But I would have avoided the problem, because now I can add the topic without any issue. Now let's talk about the Pulsar model. This model is completely different. Pulsar doesn't distribute data into partitions, but only into segments. New messages at the end of the topics are written into a segment. When the segment reaches a certain size, it is closed and a new segment is immediately created to store the new messages. This segment rolling allows for some pretty cool things, as we will see. So here is how Pulsar will have handled this previous situation. Remember topics A, B, and C from the previous situation. Pulsar will have divided these topics into multiple segments, and Pulsar would have distributed these segments evenly across the different nodes and automatically. So as a result, when it comes to accommodating my new topic D, it's very simple. Pulsar will also distribute it automatically and will be able to use all the available storage space in the cluster. In this way, the problem I had previously with Kafka doesn't exist anymore when I use Pulsar. As long as you have enough total storage space, it just works. Much less management to do, much less hassle. So let's try scaling a Kafka cluster in the case where there is not enough space available on the cluster to accommodate new data. So we need to grow topic D, the red one. So all I have to do is add a new node, and that's it, right? Well, no, not at all. It's not that simple. If I let my topic grow, this is what will happen, an incident. In reality, I shouldn't have done that. Let's roll back to the previous situation. I should have followed a multi-step plan. First, of course, I should have added my new and empty node to the cluster. But then, after adding my node, I should have reassigned the partitions of several topics as if I were, playing Tetris, the Tetris game. To do this, I have to split topic 4 into 4 partitions instead of 3. And I also have to move some partition to the new node to get a balanced distribution of the data. And only then can I start to accommodate my new data. And the problem with that is that all these partition reassignment operations, all the data movement can take a long time. We are talking hours or even days for the largest clusters. It has a very strong impact on the performance on the entire system because it consumes a lot of network and I/O resources. And since it consumes resources, it can also be very expensive. So it's a shame. With Pulsar, it's completely different. So as a reminder, when you need to add more processing power, you add a new broker node and boom, it's done. And when you need more storage, you add a new booking node and boom, it's done. Pretty straightforward. In the previous situation, when it comes to providing more storage space for new messages in topic D, since new messages are added to new segments, the new segments are open on the new node and we have the storage space immediately available. We don't need to play Tetris to move partitions around. We don't have those problems with Pulsar. So now let's talk about how data is replicated. Because there are no partition replicas, but instead there are segment replicas. Pulsar distributes these replicas among the bookkeeper nodes. So in my example here, I have a topic containing 5 segments and I have configured the replication factor of 3. This means that each segment is replicated on 3 different nodes. So if I lose a node, I haven't lost any data. In my example, segments 4 and 5 contain data that is currently being written or read. And this is recent data that needs to be read in real time with the best possible latency. So it's beneficial to store it locally on high-performance disk. However, the other segments contain cold data that will be read later by a batch process, for instance, in several weeks or even months. We don't have the same requirements for this. It's cold data. But it's a waste to use high performance and thus expensive local disk to store this cold data. Once the data becomes cold, it becomes advantageous to move this data out of the cluster and transfer it to cloud storage like S3, for example, which is much more cost-effective and virtually unlimited. This thing is called tiered storage. So unlike the open source version of Kafka, the tiered storage in Pulsar is production ready and has been used in production for many years. So we've seen what happens when you lose a node, but what if you lose a whole region or a whole data center? Never happens, right? Yeah, it does happen. That's where geo-replication steps in. Geo-replication provides disaster recovery. So we have several clusters deployed in different regions or different data centers. And if you lose a region, you can recover from it. Pulsar can replicate the data to different regions automatically in a bi-directional way. And this is a built-in feature. So you don't need Mirror Maker or Cluster LinkedIn or any other additional software. Setting this up is basically about configuration. Now, I'd like to introduce another very cool feature of Pulsar, multi-tenancy. Multi-tenancy allows different departments or teams within an organization to share a Pulsar cluster while keeping their data isolated. For example, I don't want the marketing team to have access to the finance team's data. And if one team consumes a lot of resources, I don't want that to impact other teams using the same cluster. When using Kafka, we tend to solve this by creating a different cluster for each team, but that's not cost effective. The benefits of multi-tenancy include easier management, as you only need to operate a single cluster for multiple teams. Plus, sharing resources can lead to a significant reduction in the number of nodes in your infrastructure, which save on costs. Pulsar is designed for that. This is a built-in feature. So now you could say, well, Julien, Pulsar has impressive features, but in my company, I have an existing software ecosystem. I'm sending or consuming messages with Kafka and RabbitMQ. I have a bunch of microservices, and I can't rewrite all of them to migrate them to Pulsar. Well, I have good news for you. Pulsar has a high level of compatibility, and I'll explain that right now. So messaging and streaming involve clients and a broker. They communicate using a protocol. Pulsar provides its own binary protocol, but with the addition of protocol handlers, Pulsar becomes compatible with Kafka clients, RabbitMQ clients, and MQTT clients. So by leveraging your existing apps, you can avoid the need to rewrite everything and ensure a seamless migration path. To write client application using the Pulsar native protocol and benefit from all features, you have many Pulsar clients libraries available. You will surely find one for your favorite language. So don't hesitate to check out hub.streamnative.io, where you find a wide ecosystem of connectors, libraries, protocol handlers, etc. When it comes to choosing a technology, open source is key. Some of the benefits of choosing an open source technology are sustainability, avoiding vendor locked-in, and community support. And Pulsar, of course, is open source because it's Apache Pulsar. All these features are presented are available in open source, so if you download Pulsar, you'll have all of them. This is great because you don't depend on a specific vendor. You're free to call a vendor to provide the Pulsar as a service like Stream Native, or you can manage a Pulsar cluster by yourself. There is no vendor lock-in. Now about the community. There are more than 600 contributors to Pulsar. and there are more making contributions to the ecosystem surrounding around Pulsar. The entire Pulsar code base is growing year over year. That's amazing. The number of Slack members is about to reach 10,000. Actually, it already reached 10,000. There is a really rich and growing body of knowledge, of questions and suggestions. So who uses Pulsar? Pulsar adoption is quite large, with more than 1,000 companies using it all around the globe. Okay, so now let's take a look at the history of Pulsar at a glance. Pulsar was developed by Yahoo in 2012 as their cloud messaging service to overcome both Kafka limitations and traditional MQ broker limitations. It then went open source in 2016. By 2018, Pulsar had graduated to a top-level Apache project. Since 2019, there's been a surge in the Pulsar community's growth, with rapid adoption and an increasing number of contributors. And it's worth mentioning that Pulsar has been in production for over 10 years. This means that it's a battle-tested project. It's proven to be robust and mature. So here is a quick recap. Pulsar is a unified messaging and streaming platform, handling both patterns, both semantics at the same time, so you can have only one platform to manage. Pulsar is doing great at both scaling and being elastic because of the separation between compute and storage, and because of the partitionless storage model. Pulsar ensures the durability of the data and can offload to external, cheap, and unlimited storage. Pulsar has dual replication built in, which is great for disaster recovery. Pulsar is natively multi-tenant. Pulsar is compatible with the software ecosystem. And all these great features are available as open source, so you have no vendor locked in. All right, so that's the end of my talk. I hope you enjoyed it. So thank you so much for attending. If you have any question, I'll be very happy to answer. So feel free to scan the QR code on the left to contact me and to get access to additional resources. Feel free to try out Pulsar by downloading it. I'll be very happy if you try out Pulsar, and let's connect on Twitter or LinkedIn. So now I'll be very happy to answer your questions.
Thank you for the lovely topic, Julien. It was very interesting. One question I have is, why do you think a company would stick to Kafka, even when presented all of the arguments that you presented in your topic? What would make them pick that over Apache Pulsar?
Well, would they stay on Kafka, right?
Yeah.
The question. Well, I would say because they not well Pulsar. I would say because of the kind of an inertia when you're acquainted to a given technology, and I would say also because the Kafka community is a bit larger than the Pulsar community, so that can be a bit you might be not so confident of the size of the community of Pulsar, but while it's important to know that there are thousands of organizations that adopted Pulsar, but that's still the community is not as large as the Kafka one, for sure. And behind the Kafka world, you've got huge and recognized vendors like Confluent, for example. There are some Pulsar vendors, but they are not as I would say as huge and well recognized for now, compared with the Kafka ecosystem, for sure. But it's important to know that despite of that, you've got a huge and very vibrant community around Pulsar, so you should not be afraid of picking the right technology for what you need.
Okay, and we have a question from the audience as well. What are the downsides of Pulsar?
That's a very good question. I will say that so Pulsar is a great technology for sure, but I will say that Pulsar has an architecture that is, a bit more sophisticated than Kafka, because you've got two different layers. You've got the bookie nodes, and the broker nodes. So that two kind of nodes minimum. You also need a metadata store and coordination, a distributed coordination system. So we use Zookeeper, but we are going to to switch to an alternative. But there we still need the coordination and metadata store. It means that you end up on 3 different node technologies. So that can be slightly more complicated to manage because of that. So on one side, you benefit from all those features on Pulsar. On the other side, you've got quite a bit more of complexity to manage compared with a small Kafka installation. So if you have a predictable workload, you don't need so much elasticity and you are only doing data streaming, then Kafka might be the right pick. But if you need multi-tenancy to save on infrastructure cost on a large scale, and you also need to save on cost because you will end up with only one platform to manage, then you should definitely consider Pulsar.
So it could be a bit daunting that you have to learn a new system as like a barrier of entry. I wanted to check at some point during your talk, like how would I run this on AWS, and I noticed that Stream Native is actually offering that as a managed pay-as-you-go service to manage the Apache Pulsar for you. So that should make it a bit easier, because when with the cloud, everyone's used to convenience. Because vendor lock-in is one thing, but I would rather have CapEx than OpEx. I don't want to spend brain power and people on operating.
Sure, for sure. Yeah, my talk was more focused on the open source Apache Pulsar. But of course, feel free to ask a vendor to manage your Pulsar installation, because that's the goal of those vendors, to to simplify your life and to simplify this management. So when you manage a Pulsar using the hosted managed offering of Stream Native, well, you don't need to worry about this infrastructure complexity, because all of this is managed for you, and at the same time you benefit from the multi-tenancy, the unified messaging and streaming, the elasticity, which is very important, and all that stuff.
Okay, awesome. So what advice would you give to people who want to run this on their own without using a managed provider? So let's say they have a private cloud that they want to run this in. What would be a good way to upskill so that you can run it yourself?
So you've got 2 options. I would say the first one is that you can also ask vendors like Stream Native for a private cloud offering. So Stream Native can provide you with software that will help you manage your cluster, but that's your own resources on your private cluster, all right? And the second thing is, if you really want to manage all of that by yourself, then feel free to ask the community. We've got documentation on pulsar.apache.org, and we've got a community Slack with more than 10,000 members that will be very happy to help you get started.
Okay, so basically documentation, community. I'm assuming there's online video trainings available as well.
Yeah. You've got, for example, we've got some videos for freely available videos on the Stream Native YouTube channel, for example. But you can also find, other videos, and feel free to also check out my profile, the QR code on the left. You will find some interesting links.
Okay, adding it back. All right. Well, Julien, thank you very much for the very informative talk. Thank you to the audience as well for the questions. And now we have a 1-hour lunch break after this talk. So see you again in 1 hour.
See you. Bye.
Thank you.